Bismillahirrahmanirrahim. Assalamu alaikum. Today we will cover fifth week lecture number 9 and 10. In the previous lecture number 6 and 7 and 7 and 8, we have done numericals related to pressure volume work, and we also learned different thermodynamic process: isochoric, isobaric, isothermal, adiabatic, and polytropic process. Basically, this numeric I will not give you this numerical for its solution because it's solved by double EES calculator. I just want to show that the polytropic process is not only four processes that has been discussed in the previous lectures. There are numerous processes can be performed by changing the values of n. As you know that polytropic process is a general process that can be applicable on numerous number of processes by changing of value of n. The general value of n are n is equal to 1, that is isothermal, n is equal to 0, that is isobaric, n is equal to infinity, isochoric, and n when n value is 1.4, it's 1.4, then it's adiabatic. So by changing these values, you can see that in this numerical it is solved by EES calculator for numerous values like n, 1.0, 1.32, and having numbers of volume and pressure values. On that time we have only solved from process 1 to 2, but you can see that here are number of numbers of points between this process. So these lines shows different n values, so n is also shows different path. So just for your information, in future you might say that there are only four polytropic process, but it is not right. There can be numerous polytropic process by changing values of n. 4 are general and 4 are prominent in thermodynamics. One more confession I would like to say that polytropic any external forces change the polytropic process doesn't require any external pressure or external work or external forces. The process which can be done only by its own reaction of gases, it is called polytropic process. For an example, we have a piston cylinder device and it is containing mass. By mass, this piston will decrease the volume, increase the pressure. If it is an isothermal, the temperature is constant. If it is an adiabatic, the heat transfer is constant, but there will be no variation in the forces. When we change the variation, when we apply the variation of forces, then it cannot be the polytropic process, and it will not follow this path and not follow this equation. For an example, if I remove this weight, and attach a spring system and heated this piston cylinder device, I am raising the pressure over here. It will do some work, so forces will change rapidly. The different position of a spring has different restoring force, so the forces on this piston is changing varily, so it is not called to be polytropic and it will not follow this equation. So this confusion I would like to remove in this lecture. Let's move on. I hope you will understand what is difference of polytropic process and non-polytropic process. What is not removing? Yes. Now let's revise the previous work. We have discussed, and we also did one numerical, very short numerical. Basically, we have to find out the volume and pressure in this previous numerical. Let's see. Yes, we have done this numerical, very short numerical. Yes, we have to find out pressure and the volume of the tank by the help of A4 graph, that is steam table, saturated steam water table graph. Let's revise further. As you see that how this wet dome is produced, it is not physically this wet dome. We join all the saturated point at different pressure, like in this previous. When we join, first of all understand the behavior of the gas. Let's revise again, it will be easy for you. First of all, when we heat the liquid, in the general term, but in the thermodynamics it is called compressed liquid, the volume will increase until it reaches the its boiling point. At that pressure, it is a vapor pressure. If we lower the pressure, the boiling, this could be like this. If we reduce the pressure, the boiling point also reduce. So first of all, it is reaches to the boiling point. When the boiling point achieve, then the phase change process start. The water is converting into the steam until the whole water converts into the steam. Then it is again reaches to the saturated point. It is a saturated vapor point, it is a saturated liquid point. But when we make this operation with the different pressure, like this, like in this diagram we have done 0.01 megapascal, 0.1 that is 1 atm, 1 megapascal, 8, 15, 206. We get different saturated liquid and saturated point. So I am just revising it because some student might not understand the wet dome, the region. So I just revise that again. So by joining this line, we get this wet dome, and this wet dome differentiate the left side liquid region. Inside the region we have a mixture saturated liquid vapor, and right side it is saturated vapor. And we have four different graphs. One graph for the compressed liquid, one graph for the superheated vapor region, but for the saturated liquid vapor we have two graphs, that is A4 and A5. The pressure with respect to pressure and with respect to temperature. As shown here, that is A4 table for the temperature variation in a general order, and A5 in the pressure in general order. Both are the same, but their arrangement are different. One is arranged in a proper manner with respect to pressure, and one is arranged with the proper manner with respect to temperature. So if you have a temperature, you can get the right pressure, and if you have given initial value temperature, you get the initial correct pressure. Anyway, let's move on. Today we will study one more thermodynamic properties, that is quality of steam or dryness fraction. In the previous lecture we also discussed that in the steam table we can get the value this by subscript of f, and we get the value of this by subscript of g. But what about this values? If we find out at the middle of this, we have to find out the quality of steam or dryness fraction. And we also learned the equation H is equal to HF plus X HFG. So this is called quality of steam. At this stage it is 0, at this stage it is 1. So when we have a saturated liquid, we have 0 quality of steam, and when 100% steam is converted to the steam, then the quality becomes 100% becomes steam, water becomes steam. So this is called dryness fraction, and we also discussed that Fg. So this is dryness fraction that has been also described in previous lecture by the equation H is equal to enthalpy is equal to saturated. I write it again here. If we find out the value of this, like we have a quality of steam is 0.5, then the enthalpy will be HF plus X HFG. By this equation we get the values in between the wet dome, and in the saturated vapor graph we on that particular, because it in this point, at any point the pressure will become same. So for any pressure we at any graph we get these two values. We just need to know the quality. Once we once we have known quality of steam, we can easily calculate the enthalpy of steam. And in practical system we calculated this values x with the help of experimental setup. There is a particular, if you come in the mechanical steam lab, you can see the actual apparatus which is calculating the quality of steam, and the mechanical engineers or mechanical engineering student also did practical to calculate the quality of steam. I also heading this practical labs of third year of mechanical engineering, and also calculate this quality of steam. And even in the when I taught this subject to electrical or electronics, I arrange the visit of a student to this lab and show the actual system of energy conversion from point of water to steam, and then how the steam is converting electricity. But due to the COVID limitation, I cannot bring you all people to the mechanical engineering lab, but still in the end of this topic I will show I will attach a particular animation and video that by which you inshallah you will get the idea how these are working in a practical scenarios. So anyway, you get the answer. The x is the quality of steam. The short formula of this is mass of vapor divided by mass of total. If we get the if we get the mass of vapor, and if we get the mass of total, we can easily calculate the quality of steam. Let's suppose like at this point we have the total 1000 kg of steam, and at this point the mass of vapor is 70. So by dividing this you get the answer 0.7. It's very simple. But an experimental setup, there is some apparatus which is calculating this mass of steam. It is not very easy. By the formula it is very easy, but actually calculating this total mass is very easy. In the initial state you can weight the water or can calculate the volume of water. So by that density you can get the total mass, but to calculate vapor it is very different, and we have a special apparatus to calculate this vapor. Anyway, by definition the ratio of mass vapor to the total mass of mixture. And what is the purpose? To analyze liquid vapor mixture properly, we need to know the proportion of liquid and vapor phases in mixture. This is done by defining the quality of steam. One more important parameter is that we also want to calculate this quality of steam, because we can in some machines we cannot fed the steam with the bad quality. Like if we send the quality of 0.7, it means it has 30% of water droplets, and when the water droplets hits any solid surface, it erode that material or metal. So it is a very harmful for steam turbine blade, because turbine blades are running very high RPM, and the steam flowing between the steam turbine it has very high velocity. So by very high velocity of water droplet hit when hit in blade of the turbine or metal, it erode that metal. So it's very harmful. But at very high velocity, steam has not a high saturated weight, so it will not damage metal. You can get the imagination by which when you pass very high air to any blade, it will rotate the blade but not erode the metal. But you can have experiment in which we mark water with the high velocity to the stone, so it cut stone. So when the water goes with the steam and hit the blade, it acts like that, and it's harmful for the steam turbine blades. Anyway, let's move on. I thought you I hope you understand the idea and the quality of steam, its application. We have done this numerical. Let's move on. Now, latent and sensible heat. Both are the heat, but we differentiate with the process. By definition, the amount of energy absorbed or released during the phase change process is called the latent heat. When the I'll show in this diagram. By definition, the amount of energy absorbed or released during the phase change process is called latent heat. For example, the amount of energy absorbed during the melting is called latent heat of fusion. For water it is 333.7 kilojoules per kg at 1 atmospheric pressure. And the amount of energy absorbed during vaporization is called latent heat of vaporization. For example, water has 256.5 kilojoules per kg at 180 m. So you can get what is the latent heat. Latent heat is nothing but the energy required to convert or to convert one form to another, or the energy absorbed or released during the phase change process for any substance. For process one, it is a melting process. The solid form converts into the liquid form. So converting, for example of water, when the ice is becoming a water, when the ice is change the process from solid means ice to liquid, it is latent heat of fusion, and for that only little amount of energy is required. But when the water liquid phase convert into the gaseous phase, it is called latent heat of vaporization. But for this energy, for this process, you need high energy. That's why we can easily convert water into steam at 1 atmosphere. We have ample temperature, like in the room temperature is 25, so water converts into ice, and in this process 333.7 kilojoules of energy release, or gain by this ice, so it converts into the water. And when we need to convert this water into solid, we need to put the 333.7 kilojoules per hour cooling energy, like for the refrigerator. Like in refrigeration, we also need to provide energy, so we need to provide this energy to convert that water into the ice. And when we convert the liquid into the gas, we need to burn or get the energy from our natural gas coming into our home, and in industry it is gained by coal or diesel, HFO, heavy furnace oil, or natural gas. We burn that natural gas and give that much amount of heat to the water to convert that water into the gaseous state. So I hope you get the idea. Now the remaining heat is sensible heat. The amount of energy absorbed or released during the temperature change process is called sensible heat, because you know that in these two processes temperature becomes constant. You are providing heat, but the temperature of the body is not increasing or decreasing, but remaining the process of phase change, when you applied the heat, it will change the temperature. When you are giving heat to the system, the temperature is increasing. When you releasing heat from the system, like in refrigerator, you are decreasing the temperature. Like for in this diagram, you can easily understand this diagram. This portion is latent heat of vaporization. Okay, we don't have the graph of liquid to ice to liquid, but we have a graph of latent heat of vaporization. You can get the answer. When you are providing heat in this process, it is called to be latent heat of vaporization. When you are providing heat in this time, it is called sensible heat. And when you are giving heat in this process, it is also sensible heat. When the phase change process is called to be latent heat. And we have two kind of phase change, solid to liquid and liquid to gas. So we name two kinds, latent heat of vaporization and latent heat of fusion. So I hope you understand. Let's move on. Yes. Now this is the last numerical of this steam phase change process, and after that I will add some animation and video so you will understand the actual process behind the power generation from steam, from water to from the state of water to the steam, and then how the steam is converting that much amount of energy into electrical energy. So first read out that numerical. A piston cylinder device that contains 25 gram of saturated water vapor that is maintained at constant pressure of 300 kilopascal. A resistance heater within the cylinder is turned on and passes a current of 0.2 ampere for 5 minutes from 120 volt source. At the same time, a heat loss of 3.7 kilojoules occurs. Find the final temperature of steam. Now for this particular system, you get the physical setup as well as the pressure volume work graph. Like this is wet dome. The what he is telling that it is a you should understand that when it is showing the state 1 here, it means that all the substance inside the cylinder is steam, and it is also telling us the name saturated water vapor. So even if they didn't show this diagram, you can get the idea that what kind of substance inside the cylinder is saturated vapor. It is mean that it is 100% steam and has a quality of 1. So when we yes, that is maintained at constant pressure. So even after that the graph works like that. So when we it is temperature versus entropy graph. So the graph act like this. So it is a constant pressure on TS gram, but now it is a pressure volume work. So at constant pressure, when the heat is applying, the volume will increase. It is telling that it is maintained at constant pressure. So pressure becomes at constant. That's why it is moving like a straight line from 1 point to 2. So when you heat up that system, the cylinder moves on, the pressure kept constant. So amount of heat you are giving, it is going basically towards the work, pressure volume work. Or in other means, you can it is going towards the internal increasing the internal energy of the steam that can be converted into the work. So now to solve this equation, we first form a data.